regardless of what you describe. Stay inside. You know, if you need stuff, groceries better for you.
All right, good afternoon, everybody. Welcome to the WRS 8100 seminar. Today our speaker is Kade Flynn. He's a master's student working with John Baker and Brent Dalzell in the USDA WRS. And he'll talk to us about agricultural landscapes and nitrogen transport. Can everybody hear and see the screen? All right, thanks, Fabian.
All right, hello everyone. Excited to be here and share some of the work I've been involved in the past couple years here. Going to start off with a picture on a Friday afternoon. I'm going to refer back to this image kind of throughout the presentation. Well, let me start a timer real quick here. This image kind of encapsulates kind of the three components that are sort of motivate the work that our work centers on, these three different components and perspectives. The first two being this headwater agricultural stream and the landscape. In the systems we're working in southwest, south central Minnesota, there's a lot of tile drainage and channelization. So generally a lot of movement of water from the landscape to these headwater agricultural streams. So there's this really pronounced relation between what you can measure in the stream and what's happening on the adjacent landscape. The third component is this sampling platform that I'll be talking about more, that we're using to measure in these headwater agricultural streams. And using this data we collect, we're trying to gain a better understanding of how what happens on the landscape influences water quality at this kind of high spatial resolution. Before getting into these three components, I kind of want to take a step back and position this work a little bit and talk about these three different reference frames for measuring water quality. In the bottom right-hand corner, you have fixed site Eulerian sampling, where you have a continuous temporal record that you're measuring, but it's just at one location. And the opposite of that is this snapshot synoptic sampling, where you're measuring across space, but at a single point in time. And then you have your Lagrangian sampling that kind of sits in between those two. So the fixed site Eulerian sampling, think like a gauging station at a watershed outlet. So you have this continuous temporal record, but it's just at a single point in space. This snapshot synoptic sampling, you have measurements that cover this really wide area of space. This is Lake Minnetonka. This is a screen grab from Lake Browser, which is a University of Minnesota tool. But all of this was captured at a single instant in time. Kind of in between these two, you have this flow path Lagrangian sampling. So this is an image of nitrate concentration measured along a stretch of stream. So you have this spatial variance, but this data was collected over a period of several hours. And this flow path Lagrangian sampling is sort of the data collection method that we're employing in this work. And it's not really anything new. There are several, it's relatively new, but there are several other people who have instrumented different platforms to collect this sort of data. So a couple examples here. We have the hydrosphere, which is essentially this buoyant orb that you could place in the water. It has all these different water quality sensors on it, and it would kind of float passively down a stream. You have the Flynn from the University of Wisconsin, the fast limnological automated measurements. So this system's on a speedboat using very similar sensors, but it's collecting data in large lakes, large streams, rivers, and it's kind of this flow path sampling, but it's not passively floating down a water channel. So this is kind of this gradient of temporal temporal variation here. The flame could maybe be more of this snapshot measurement approach. We have these other two systems, a canoe-based flow path sampling device and a drone-based flow path sampling device. So unlike the hydrosphere, if you're measuring in a stream with both of these systems, you'd likely be actively paddling, so it's not quite completely passive. But unlike the flame system, you're not moving as fast as a high-speed boat in these lakes and streams. And that's kind of, very similar to this reference frame that we're using in these headwater agricultural streams. But there are some unique challenges to measuring the systems that we're interested in measuring it. So these headwater agricultural streams can be characterized by narrow channels and shallow water, which would pose a problem for even a canoe oftentimes. Wetlands, debris, and fences would sort of pose a problem for a remote operated drone, culverts as well. And then obviously something on like a high powered boat just really wouldn't work in this system. So to kind of get around some of these challenges, Ryan Felton, who worked on this project, he was a master's student in the program before me, sort of introduced this novel sampling platform based on pack raft, pictured here. So these pack rafts are often used in like backcountry Alaska or with bike packers or backpackers, and you can pack them down really small and they inflate and are able to carry a lot of weight. What's pretty unique about them compared to like a regular, canoe or kayak is that the bottom's flat. So, there's no real hole, so you can float in very shallow water. They're extremely durable and lightweight, so navigating over those obstacles like debris jams and fences is possible with this system. And much like many of the other Lagrangian sampling devices like the hydrosphere or that canoe or drone-based system, we have these water quality sensors, these optical sensors that hang off the boat and measure in the stream. These are hooked up to this cooler that contains a data logger and a GPS unit. So each time one of these sensors takes a measurement, it's saved on the data logger along with the GPS coordinates for that point it was measured at. So everything's spatially explicit. In addition to these sensors that hang off of the boat, we have this thing called a Bandolero discrete sampler. It's a pretty cool device. So with the push of a button, we can activate this little peristaltic pump that's hooked up to a line running into the water and suck in a water sample. We can take those water samples back to the lab and use them to validate these sensor measurements or to measure things that we can't measure with the sensors, like dissolved reactive phosphorus, which I'll be showing a little bit of that data later on. So we have this ability to measure in these headwater agricultural streams. And I want to talk a little bit about the motivation for the work and why we wanted to develop this sort of system. So, one of the ways to address issues related to nutrient loss from these agricultural systems is to change land management on the farms at the field scale. There are tools like the Agricultural Conservation Planning Framework, ACPF, which is an important part of our work, that provide this watershed approach for field scale conservation planning. So the ACPF uses high resolution geospatial data along with local knowledge to provide options for conservation practice type and placement. And this map shows an example output of ACPF in a watershed. Really what I'm trying to show with this image here is that the placement and the recommendations from these geospatial tools like ACPF occur at a pretty fine spatial resolution. So there are certain areas in the watershed that have been identified as, potential spots to implement some conservation practice because of, specific characteristics of those locations. So if you contrast this sort of option, this solution that we can have for reducing nutrient loss with one of the ways that is often monitored, which is using this Eulerian reference frame at a watershed output, where you have this continuous temporal record at a single point in time. And so understanding the influence that potentially one of these, field scale conservation practices is having on water quality can be really difficult when you have this big spatial discrepancy. So that's kind of why we've implemented and are trying to use this pack graph based approach to kind of bridge that gap. The data I'm going to be showing today are from these two watersheds, High Island Creek and Crane Creek. They're both dominated by agriculture. As you can see, all the brown is cultivated cropland. Crane Creek is kind of unique, and at the headwaters, there's this big lake or wetland complex. So as you move downstream and your catchment area increases, you have this effect of increasing the proportion of cultivated land draining to each point in that stream. And to start, I want to sort of just show what the data from the sampling platform looks like, how we can measure in these headwater agricultural streams. I'm going to do that in Highland Creek, go into this middle section of the watershed. It's characterized by Highland Lake and several flow through wetlands that the stream goes through. And so I showed this image before, but want to look at it a little more closely. So we see, this is the data output that we get. We make a paddle and we collect these nitrate concentrations in these streams. We see as we move from upstream to downstream on this particular day, you see this kind of decrease in nitrate concentration as you go along. These changes in what we measure in the stream happen at these kind of distinct points. So here we have the outlet of High Island Lake draining into the stream. Here we have a series of flow through wetlands. And at both those locations, we see these decreases in nitrate concentration. So everything that we're measuring in the stream really is related to what's happening on the surrounding landscape. And what we've done is we've taken the sampling platform and we've gone, bi-weekly for several years, and we have a lot of this data. And so you can look at how these spatial measurements change through time. So on this right figure, we see channel distance from the watershed outlet on the x-axis, nitrate concentration on the y-axis. And each of these lines, these different colors, represents a different sampling date. The colors on this figure correspond to the colors in this hydrograph. So we see that we've captured, through this sampling, a variety of different flow conditions at a variety of different times of the year. And you can see that the stream behavior changes with flow and season. Just to point out a couple examples of that change in response, we see the lake outlet of Highland Lake that I pointed out. On April 11th and September 10th, we see this decrease in nitrate concentration as we go past that lake outlet. So there's some sort of likely diluting of nitrate concentration happening. But at other times of year, at other flow regimes, that's not the case. Either the stream was higher than the lake, so the stream was actually feeding the lake, or the lake was still frozen or something like that. So there's no real observable effect there. You also see that, for instance, wetland C, one of these flow through wetlands, as you paddle through that on September 21st, you see this decrease in nitrate concentration. But at other times of the year, there's almost no effect. So whether that's dilution or in-stream processing, that changes throughout the season and throughout years. And looking at another variable that we measured, dissolved phosphorus, we see a similar thing, where as we go through these wetlands and lakes at different times of year, there's different things happening. So sometimes these lakes are kind of little hot spots where we see this sharp increase in dissolved reactive phosphorus, and then drops as we go through the stream. So with this system, we can collect a lot of information on these environments that prior to this sort of sampling approach, you wouldn't really know what's going on at these locations. But I've sort of pitched this sampling platform, and one of the questions that we're really interested in is how we can use this to better understand what happens on the landscape and how that influences the water quality. So I want to kind of discuss that point a little bit. So going over to Crane Creek, like I mentioned before, Crane Creek's unique in that this section that we paddle starts in this headwaters where you have this lake and wetland complex. And as you move downstream, you enter regions that are dominated more by cultivated crops. So if we look at a section that we've paddled in Crane Creek, you can see that effect. So here we have nitrate concentrations, channel distance to the watershed outlet. And we see, as we're closer to that wetland and lake complex near the headwaters, you have these lower nitrate concentrations. As you pass these ditch confluences, you have these sharp increases in nitrate concentration within the stream. You also have kind of this gradual increase along certain sections as well. So we can measure the stream using this pack graph sampling platform. But to connect the landscape to the stream, we need to have a representation of the landscape at each of these measurement points in the stream. We can represent the land using the same high-resolution geospatial data from ACPF. So what we've done here essentially is use some of the geospatial tools and data in ACPF to delineate catchments for each of these points in the stream. And we have information on sort of the land characteristics within each of those catchments. What I'm showing here is the proportion of cultivated land use. And you can see, this proportion of cultivated land use increases as you move from upstream to downstream. And this increase is most pronounced at these ditch confluences. So you float by a ditch and suddenly your catchment area increases. So you're draining a much larger area in the landscape. That additional area that's draining to that point that we've measured happens to have a higher proportion of cultivated land use. So you see this sort of sharp increase. If we overlay the two, we see kind of this really, really tight correlation between what's happening. And when we first looked at this was really exciting to us. So these same locations, these same ditches that we see these sharp increases in nitrate concentration, we see that there's also this increase in the proportion of cultivated land use draining to those spots. And this change happens at these ditch confluences, but also more gradually as we paddle along these sections. So, we see these gradual increases in nitrate concentration corresponding to these gradual increases in the proportion of cultivated land use draining to each of those points. So we have this system, and we have this system to measure these nitrate concentrations in the stream. And we have this completely separate data set of what's happening on the land. And we see that there's this really, really interesting interaction between the two. So, we see this in Crane Creek. And so we want to kind of look further at this connection between the data that we're collecting using our sampling platform and the landscape, to try to use it to really get a better understanding of the processes that are happening. So, can we really quantify the effect that the landscape has on water quality at this really high spatial resolution? So to look into that, I want to go back to Highland Creek, this time in the headwaters. So the headwaters of Highland Creek are just dominated by cultivated cropland. There's also much more artificial drainage. So there's a lot of ditches, a lot of tile lines in this section. And unlike Crane Creek, there's not really this gradient of the proportion of cultivated land use in this section of the stream. So we decided to look at this other metric, the nitrogen intensity. So using the same high resolution geospatial data from ACPF that we use to get the proportion of cultivated land use, we get this nitrogen intensity metric. So we have this estimate of the nitrogen input per catchment area based on a history of crop rotations and fertilizer recommendation rates. And we have the catchment area. And so we just divide those two to get this nitrogen intensity value. So it allows us to compare, regions of the watershed that are, may have a similar amount or very different amounts of applied nitrogen, but be very different sized catchments. So for the same mass of applied nitrogen in a smaller catchment, you'd have a higher nitrogen intensity. In a larger catchment, you'd have a lower nitrogen intensity. So looking at a section of stream that we've paddled in the headwaters of Highland Creek, you can see this black line is the section of stream we paddled, starting in this judicial ditch and then entering into Highland Creek and ending at this downstream location. You can see, these polygons here are the nitrogen input on the landscape that we've estimated using crop rotation history and recommended fertilizer recommendation rates. And so, you see that there's some variation. This is mostly due to, certain areas having a higher proportion of corn compared to soybean being grown. So that's really about all the variability that we see in this landscape. And on the right hand, we see this figure that's showing land nitrogen intensity on the y-axis and the distance to watershed outlet on the x-axis. And we see, I want to go frozen screen here. There we go. We see that these locations where you have these catchments of a different nitrogen input draining into the stream, we see this corresponding drop in the land nitrogen intensity at those points, right? And this happens, kind of drastically, but also more gradually as well. We can compare that kind of landscape data to this in-stream data that we've measured with our sampling platform. And we see this very similar pattern where we paddle past these areas that are draining these regions in the landscape, and we see these decrease in nitrate concentration. So, first thing we decided to do was kind of do a simple model to look at how this nitrogen intensity value is affecting the nitrate concentration measured in the stream. And we see that the stream nitrate concentration increases as the land nitrate intensity increases. Did a test, performed leave one out cross-validation to test the model performance. So this simple model here. So basically what we did, what happens here is the response variable is removed one at a time, and then the model is used to predict that response variable. And this figure on the left is showing that comparison of what we've measured in the stream and then what we can predict with this simple model of nitrate concentration explained by nitrogen intensity. And you have this one-to-one line here, and so you can see, there's this clustering around to this one-to-one line. So generally, this simple model seems to be explaining pretty well what's happening in this system, which makes sense. It's nothing surprising that when you have more nitrogen applied to the landscape, you have more, a higher nitrate concentration in water leaving that landscape. But we need to kind of be cognizant of sort of what we're measuring. And that's these parcels of water within the stream. And so at any point that you measure in the stream, that water, some of it is flowing from an upstream location. And so there's going to be some relationship between these upstream locations and these downstream locations. We can account for that using these spatial stream network models. So, we can use this special class of these spatial models that's designed for branching networks. And the necessity of this special class of models is kind of depicted in this image here. So classical spatial statistical models, derive spatial relationships based on Euclidean distance. But in streams, you're confined to these branching networks. And so you can have these two cases. You can have 2 points that are flow unconnected or 2 points that are flow connected. And so if we look at kind of the relationship, the spatial relationship between the nitrate concentration that we measure in the stream we can use a semi-variogram to kind of gain information on whether or not there's spatial autocorrelation here. And we see this really distinct pattern. So as the distance between points increases, the degree of dissimilarity increases, but this isn't happening randomly. And so that means that there's spatial autocorrelation in what we're measuring in the stream. And we need to account for that because the whole idea here is to use our in-stream measurements to inform on what's happening on the landscape, not these processes that are happening within the stream. So if we account for this spatial autocorrelation in this simple model, we can better isolate out the effect that the landscape is having at individual points that we measure along the stream. So we can perform that, run the same model, but this time accounting for that spatial autocorrelation, and perform the same leave one out cross-validation test. And you see here on this figure on the left, we have our non-spatial model results that you've already seen in these gray dots, and then the spatial model results on the black dots. When we account for the spatial autocorrelation, you see less clustering. So there's more, less clustering, and it follows this one-to-one line much better. And we compared the two models using a variety of tests, a K-Keys information criteria, the root mean squared error, and the R squared of this leave one out cross-validation plot. And we see that in each instance, the spatial model better accounted for the variability that we're seeing in what we've measured. So, we have this method to collect high resolution geospatial data and headwater agricultural streams based on this pack graph sampling approach. So we can use this Lagrangian reference frame to characterize features of the landscape and the influence that they're having on water quality. We've coupled these in-stream measurements with this geospatial tool and data from ACPF to characterize features of the landscape draining to each of these points that we've measured in the stream. And we can use statistics to inform our understanding of the landscape stream relationship. The next steps are to use this sort of analysis framework that I've presented as a way to evaluate some of these more nuanced landscape stream relationships, like potentially what is the effect of cover cropping, buffer strips, or soil texture on nitrate concentrations in the stream, and how these landscape stream relationships change with flow, season, and location in the watershed. So with that, thanks to John Baker and Britt Dalzell for guiding this project, Sarah Porter for her expert knowledge of ACPF, Madeline Conwall and Ryan Felton for their contributions. And I'll open the floor up to any questions. Monitoring the chat, so if anybody has any questions.
I have a question here in the room. You might want to repeat it. I was just wondering if you are interested in looking at the temporal variability along with the spatial variability. There may be, do those spatial relationships change over time is my question.
Yeah, so the question was, whether we're considering the temporal variability as well to understand whether or not these spatial relationships change over time. And short answer is yes, definitely. There are definitely, for example, right at melt-off, nitrate concentrations in these streams are really high. And if you look at the signal, if we paddle a section and you sort of plot it on this distance to outlet plot, it's like a straight line. At lower flow conditions late in the fall, you see a lot more variation in nitrate concentration. And so at certain times of the year, there's probably processing happening in the stream. And so, if we don't consider that, and we're trying to just understand what's happening on the landscape, right, we need to account for that, definitely. And so that's where these spatial models come in, is we can sort of create an understanding of the spatial relationships for each of these points in time and sort of account for that as we're trying to evaluate the influence of the landscape.
Kate, I got a question for you.
Okay,
Could you go back to one of your slides, with your initial, I think in 510 slides, where you have nitrate concentration with the distance? You did a good job on the presentation, by the way. I appreciate that.
okay, thanks. Yeah.
Yeah, go back and then I'll stop you.
Okay. I think I know which one you're talking about.
Yeah.
This one?
Yeah, in here, yeah, this would be a good slide. When you're looking at the concentration, say May 26,
Yes,
and you go with the distance, concentration is constant.
yes.
So does that mean every field is giving the same concentration of nitrate?
Yeah, so this section of the watershed is kind of different from that upland section that I was most recently talking about. So I'm going to go to this map here.
Okay,
So you see, yes, there is agricultural land all around here, but there's also these sort of wetlands, flow through wetlands.
okay,
And so at certain times of the year, there's changes in these nitrate concentrations as we go through these wetlands. But May 26th, when flow is really high, and early spring, March 26th, there's not really any sort of increase in residence time or much biological activity happening here. So potentially, at some of these points, there's some in-stream processing of the nitrate, but that's not happening at these dates where you have, very high flow, so water moving through these wetlands very rapidly in colder temperatures, so just less biological activity overall.
so you are saying is that upland lake or wetlands are influencing these concentrations, are dampening the concentration. Is that what you're saying?
Yes.
Okay, show me a graph where you have dip, no wetland effect. Okay, is that the one you want to talk about?
Sure.
All right, so look at the top yellow one, the brown one, and you go from 18 to 12, concentration is still constant, and you're within 5.5 to 6.5 or something,
Right.
right? You think all the fields in that area giving out the same nitrate concentrations?
These landscapes are very similar. Definitely, they're not all giving the same nitrate concentration, but whether or not, we're able to differentiate between one cornfield and another cornfield, yeah, potentially not. So overall, compared to this section, up here where you have this wetland complex, compared to this area downstream, yes, you see these differences. And you can see, when you pass these ditch confluences, you have an increase in nitrate concentration. And, you see the spike, but then it remains a little bit higher as well.
Okay, explain to me, why would the concentration go up? I mean, there's slight increase in the concentration, it's going up. I'm
Yes.
just trying to understand, not try to question what you're doing, but I mean, concentration depends upon the nitrogen load and the amount of water flow. Is that because of change in water flow, or is changing because they're putting more nitrogen out?
Yeah, that's a great question. It would be really nice with this system if we were able to, at the same resolution that we can measure nitrate concentration, also measure flow.
Right.
But we can't take those measurements, but
Okay.
we can understand, I'm not really showing that here, sort of when you pass this ditch, the additional area draining to that point. And, if you make some assumptions on, uniform water yield across this landscape, you could get an estimation of loading to better understand, whether or not this is from a higher amount of nitrogen in the water relative to these other locations, or if it's just more water entering the system.
Yeah, I think that's a part
You have other
I was
data.
wondering if concentration is just by itself is a good parameter to say much about what's happening in the uplands over there.
Yeah.
When you and Ryan were actually measuring flow, right? You don't have those data here. But
Yeah. Brent was just saying, I'm not showing this data here, but we have done paddling runs where we've gone through and actually sampled from individual tile lines and collected flow and collected concentration. And so we do know that these differences do exist here.
And have you got some kind of a plot that says this is the concentration in the ditch, in the stream or whatever you were mating, and you also had taken a sample and that comes close to it without manipulating the other way that you did with the intensity? Do you have any one-to-one correlation?
I don't think I quite understand your question.
Okay, well, you took some samples as you were going along, right? Water sample and brought
Yeah.
it to the lab and measured it, right?
Yes.
And you also had a concentration measured with a sensor without taking the ratio of nitrate intensity or whatever the nomenclature you used.
Yeah.
You have just one-to-one relationship, calibration, how good the sensor was.
Yeah. These we have done all that test, and I didn't include that in the
Okay.
presentation,
Okay.
but
That's
yeah,
fine.
these sensors, the accuracy of them can be quite impressive, and really, without them, we wouldn't really be able to have any of these Lagrangian sampling measurement
Okay.
systems, because you can't really, collect that many grab samples in a
Right,
system and
right.
take them back to the lab and measure.
Thank you, Kate. You did a very good job. Thank you.
Thanks, Satish. Question from John Niebuhr in the chat. How does the alpaca raft do in the case of barbed wire fence? Is it hardy enough? Will you eventually be able to measure flow while floating downstream? So the fence question, that image came from some of the work that Ryan Felton did when he was sort of, first developing the system. And that's a watershed that we haven't gone back to before. So it requires navigating around the barbed wire fence for sure. I think in 2 years, the alpaca raft has had one puncture, but the rafts are at a really low pressure. So if you puncture them, it's not like you get this really fast deflation. So there's some time to put some duct tape over a hole. And will you eventually be able to measure flow while floating downstream? We've thought about this a lot, and I wish we were currently able to do that, but haven't been able to come up for a system to make that happen. So hopefully in the future, but as of now, the best we have is taking flow measurements, at road crossings that we paddle past. So we have really this much coarser resolution that we can couple with our boat measurements, but currently no.
Is there any question of ownership and access? In other words, can you be prevented from going up a stream that's private owned, or how does that work?
Yeah, so the question was on access and private land and the systems that we're measuring it. I meant to mention that, but in Minnesota, as long as a stream is navigable, you have a right to be in that stream. But if we were to, step on the bank, technically we would be trespassing, and that is one of the real challenges to some of this work. Is these systems, these agricultural systems that we're measuring in, are really all private land, and so yeah, you do have to be really aware. And if we were to carry out some of this work in different states, definitely need to check into different access laws in those areas. Fabian asks, I'm curious about the increase you see in the confluences. If the landscape cropping system is similar in both waterways, How do you explain the increase? Have you navigated both waterways to measure concentrations on both before the confluence? So I'm going to go back to this slide. So here we have a confluence, and we see that this confluence drains this area. It has this gray field here is an area that's a funded conservation practice. So it's perennial crop, perennial grasses rather than corn and soybean, which makes up most of the other areas. So you see this has this effect of having this lower applied nitrogen in this landscape. And if you go back here, we see that when we paddle through this confluence, we see this drop in nitrate concentration. Oh, it must have been cut off here, but yes. So yes, you see this nitrate concentration, and oftentimes what we do is when we paddle, we will curve around and paddle into these side ditches so that we independently measure their nitrate concentration before going back into the main channel. So yes, we know that this area had relatively less nitrogen compared to the surrounding area did in fact have a lower nitrate concentration in this surface ditch. And when that ditch enters into the stream, you see there's this diluting effect. Hope that answered the question.
Yes, thanks.
I have a question.
Yes, David.
What's your intended use for all of this information? I mean, how do you think this will help us to understand or manage nitrogen better through this research? A lot of what you're saying, is rather intuitive.
Mhm.
And didn't we already know a lot of what you're doing, or is this something that's going to help us somehow do a better job in the future?
Yeah, that's a great point. So the question was sort of what's the application here? A lot of what I presented, where you have this increase in nitrate concentration, when you have more nitrogen on the landscape, is intuitive and not really any new information. My intention, in the work thus far was kind of create this framework for using this data to explore this landscape stream interaction. So, we have this method to collect data in the stream, this method to collect data on the landscape or acquire data from the landscape using ACPF. And so, and we have this method to analyze the two using an account for, the spatial autocorrelation using these statistical models. So next steps are to apply this framework to understand, kind of more of these nuanced relationships. Like if you were to convert a single field to perennial grasses from a corn rotation, would you see a decrease in the nitrate concentration of water leaving that area of the watershed? Or is there this accumulation of nitrogen in the landscape? And so kind of this attenuation of that effect. We kind of explore that within these working systems. I think there's also, ability to use this work to validate, modeling that's being done. And also as a way to, better place Eulerian sampling gauging stations where you have more of an ability to measure load or flow and concentration continuously, and you can identify points in the watershed that would maybe be more interesting to understand rather than just relying on placement on a watershed outlet.
Kade, I got one more question. You left too much time in your seminar for questions.
Yeah.
What's the sensitivity of the sensor? How many milligrams concentration?
Good question. So it kind of depends on the sensor that we're using. So one of the sensors, most of the data that I've shown is from the SCAN spectralizer. And so it has a resolution of, plus or minus a tenth of a ppm. And that does vary based on turbidity. And what we have been able to do is sort of compare that to laboratory methods for analyzing by collecting those grab samples. And so, we can apply these kind of site-specific calibrations to increase the accuracy as well.
So in this graph that you have on the screen, the gap that you were talking about, that's only about a 0.3 milligrams per liter.
Yes.
0.4.
Mhm.
So you think the sensors are sensitive enough to pick up these little differences? Just one field being a perennial grass or perennial vegetation that has such an influence.
Yeah. I mean, we've been able to validate, these sort of slight changes with laboratory measurements, and we can kind of, do a conceptual check as well to, get a better idea of whether or not that's sensor error, or if there's actually an event there. So there are times when we are paddling and the sensor comes out of water, and sometimes the measurement is kind of sporadic, but we can kind of track when that happens to sort of pull out all of that bad data. So yes.
So the point that you have close to 12.5 milligram, you have some explanation for that kind of variation?
Yeah, I do. And that probably should have been removed, but right when we pass here, there's a culvert that we have to paddle through. And so that must have been a point that was not removed.
Okay,
Yes.
It
thank you.
seems like an important contribution, gives you access to the point sources. You can quickly go in and measure outflows or tile outflows and stream inflows, where that would be difficult to do.
Yeah, right. I think, even if you have the ability to get land access, we can collect, this system's a lot more efficient than walking to a field to a specific point in a stream. So yeah, if you're interested in just a specific location, you kind of have a lot more data to work with when you take these measurement approaches.
What would the advantage be of having a robot to do all of this rather than having a person out there to collect the data? I mean, you showed a couple of robots. How do they work and how do they compare
Yeah,
to
so
what you're doing?
so this system, let's flip back to it. This drone based, it's called the Aquabot. Right, I think there's probably more disadvantages in our system than advantages to this system. So the way this is operated is you have to keep it in sight. So if you're going across this 10 kilometer stretch of stream that's full of debris flows and fences and shallow water, I don't think you would really want to just have a system that could automatically take these measurements, because you have less of an ability to sort of check what's happening and make adjustments, or pull sensors out of water so they don't get damaged. And then you also have this land access issue. So in order to not be trespassing, you really need to be staying within the navigable channel. So if you have this drone-based system that you need to walk alongside, it kind of defeats the purpose a little bit, I think, of measuring, in these systems that you wouldn't normally be able to acquire data from. Yeah. Any more questions?
All right, thank you. Thank you very much.
Yeah, thank you.
That's the end of our WRS seminar series. Thank you, everybody.
So is the fence across a navigable stream
That's a good question. Yeah,
I would be carrying fence covers.
yeah. Who knows how
Why
old
would
that
they
is?
put a fence across the?
Ask, ask her.
Might own both sides.
Yeah, I mean, this could be, in the middle of spring, so flow's really high, and in most of the year, it's dry, and yeah, so it's cow
All right.
grazing or something.
Thank you.
In Wisconsin, I